Hello students, this is Dr. DA here, and I'm going to show you this video in case we don't get to cover it in class. You are responsible for watching it and taking notes because it is part of the topics included in this unit on liquids and solids. This video is about phase diagrams, and I'd like for you to watch it closely because the animations are very helpful in understanding the different transitions between phases, gas, liquid, and solid. All right, we'll see you soon.
A phase diagram specifies the physical state of a substance as temperature and pressure varies. The diagram consists of regions separated by lines. Each region displays the conditions at which a particular phase is stable. Each line between two regions displays the conditions at which those two phases are in equilibrium. This phase diagram is typical for most substances. In general, lower temperatures and higher pressures correspond to the solid phase. Higher P and T correspond to the liquid phase, and lower P and higher T correspond to the gas phase. Let's take a closer look at the diagram and view the various parts on the molecular level. A magnified view within the solid region shows the regular array of tightly packed particles typical of a crystalline solid. Note that the particles in a solid are not fixed, but jiggle in place about their crystal sites. A magnified view of the liquid reveals a major difference between it and the solid. The particles are still in close contact, but their positions are much less restricted than in the solid, and they roll and tumble around one another. In stark contrast to the solid and liquid phases, a magnified view of the gas shows the particles far apart except when they collide. At any point along the solid-liquid line, the phases are in equilibrium. Melting and freezing are occurring at the same rate. In other words, the same number of particles are moving from the solid to the liquid per unit time as are moving from the liquid to the solid. Similarly, at any point along the liquid-gas line, vaporizing and condensing are occurring at the same rate, which means that the number of particles moving from the liquid to the gas per unit time equals the number moving from the gas to the liquid. Finally, along the solid gas line, subliming and depositing are occurring at the same rate. That is, the same number of particles are moving from the solid to the gas per unit time as are moving from the gas to the solid. Two other features of the phase diagram are important. The first is that the liquid-gas line ends at a point called the critical point, beyond which the distinction between a liquid and a gas disappears. Let's close in on this point and 2 points very close by to see what this means. At a nearby point in the gas region, the gas is under very high pressure, so the particles are reasonably close to each other. Thus, the density of the gas is relatively high. At a nearby point in the liquid region, the liquid is at a very high temperature, so the particles are beginning to separate from each other. Thus, the density of the liquid is relatively low. As these 2 points approach the critical point, the particles in the gas move even closer together and the density increases, while the particles in the liquid separate even more and the density decreases. At the critical point, the densities become equal and the phase separation between liquid and gas disappears. The second important feature occurs at the junction of the 3 phase boundary lines. At this point, called the triple point, the 3 phases are in equilibrium simultaneously. What would happen to the sample if we steadily increase the temperature at constant pressure? That is, move horizontally from left to right on the diagram. The changes depend somewhat on the starting pressure. Let's begin at some pressure between the critical point and the triple point. Starting with the solid, we increase the temperature until the solid and liquid are in equilibrium. Increase the temperature above the melting point, and pure liquid exists. Then, the liquid and gas are in equilibrium, and further heating vaporizes the sample to the gas. Suppose we had begun at some pressure below the triple point pressure. We begin with the solid as before, but heating brings the solid into equilibrium with the gas, not with the liquid. And further heating sublimes the solid to the gas. Carbon dioxide behaves this way. It has a triple point pressure of 5.1 atmospheres. Warming a piece of dry ice at ordinary room pressures of around 1 atmosphere changes it directly into the gas. Liquid CO2 is not stable at 1 atmosphere. Now, let's see the changes the sample undergoes as we decrease the pressure at constant temperature. That is, move down the phase diagram. Here, the starting temperature determines how the sample changes. If we start with the solid at some temperature higher than the triple point temperature and lower the pressure, we first reach the solid-liquid equilibrium state. Thus, the sample melts due only to a change in pressure. Then, the pure liquid exists until a further pressure decrease balances liquid and gas in equilibrium. And finally, the pure gas. Notice that if we start at any temperature lower than, to the left of, the triple point temperature, we move directly from solid to gas. Here's the phase diagram showing all the regions, points, and equilibrium processes.
Let's take a look at some examples of phase diagrams for different substances. Here on the right side, you can see the phase diagram for carbon dioxide. Notice that as the video was saying, your triple point for carbon dioxide occurs at a very high pressure. That means that under normal circumstances of pressure and temperature, carbon dioxide exists mainly as a gas. However, under high pressure, we can actually compress it to a solid. And what is interesting, if you look at line B over here, you can see that if I had solid carbon dioxide, which is what we normally call dry ice, under normal temperature of 1 atmosphere, putting it at room temperature, let's say 25 degrees or so, it's actually going to produce a transition that is a sublimation, not a melting, as we're accustomed with seeing with other solids. When they're heated, they simply melt. Carbon dioxide or dry ice solid is what's sometimes used on stage to produce what we call stage smoke. The reason is that at room temperature and normal pressures, the dry ice, which is solid carbon dioxide, will sublime, and because of its cold temperature, it'll cause some of the moisture in the air around to condense, generating the effect of smoke. Speaking of water, let's look at the next diagram here, and this is the phase diagram for water. Notice that unlike other ones that we've seen, the fusion curve, in other words, the line between the liquid and the solid, is actually slanted in a different way. So that creates an interesting experience here when you are dealing with water. Let's pick a point. Let's say under normal pressure and with frozen water, which is actually ice. Let's say over here. We are right below the freezing point under normal atmospheric pressure. You know, it's interesting. Normally, if you increase the pressure on a substance, the tendency is for the particles, the molecules, to compress, and therefore you would expect for the density to increase. So if I were to take ice at 1 atmosphere or 760 torr, a little below its freezing point, and I would start compressing it, I would expect its density to increase and become harder and harder ice. It is interesting, but in the case of ice, what's going to happen is that as it goes up, it's actually going to end up becoming liquid. Because in the case of water, the density of the liquid is actually greater than the density of the solid. We will study this in more detail later on in the semester, but the point here is that the hydrogen bonding between water molecules is so strong that it causes the liquid state to be more compact than the solid. In the ice form of water, the molecules are crystallized in a way that leaves a lot of space in between them and therefore generates a less dense structure. You know, that is good for wildlife because, as you know, during the winter months in extreme climate weathers, the water freezes, but as you can see, the water actually freezes on the top, leaving liquid water underneath the ice and thus allowing uh, you know, creatures and different forms of life that inhabit the liquid phase to be able to stay alive. And that is an interesting observation about one of the many interesting properties about water.